Welcome, everyone, and thank you for joining us today. We have three fantastic speakers lined up for you to discuss transforming urban rail transportation with 5G mobile networks. They will discuss technology issues, use cases, and challenges that confront the world as it moves to take advantage of 5G to improve urban rail transportation systems. Let's turn to today's featured speakers. Walter Quino is the Vice President of Research and Innovation at Thales Canada. He will explore the key needs and main 5G use cases for urban rail transit system operators. Boyan Subasic is the Principal Product Line Architect for Data Communication Systems at Thales Canada. He will review future mobile communication options, how to best leverage 5G, and the challenges in transforming from legacy communication systems. Chris Nightingale is the Chief Technology Officer at Guavus. He will discuss how mobile network operators can help urban rail transit operators get the greatest value from 5G by improving services, security, and customer experience. You may think of questions during the course of this webinar. Please be sure to ask them via the webinar chat system. We look forward to addressing them during the Q&A session. If you experience any technical difficulties using a web browser-based client, always remember that you can refresh the page to get back into the webinar. Also, we offer some poll questions during the session. Don't be surprised when your screen receives one of them. We'd really appreciate it if you could participate in our polls, and we promise they will be interesting. With all that said, I'd like to ask everyone but Walter, our Vice President of Research and Innovation at Thales Canada, to turn off their video and audio. Walter, the floor is yours.
What I'd like to do is step back a minute to talk about trends in urban transit, just look at the progression of change and show you how the pace of change is actually going to have a big impact on the technology and on the communication systems of the future. If we look at the timeline for transit, it goes back to the 1800s. The first subway system was in London in 1863. The first one in North America was in New York in 1904. And that was where we saw the first types of signaling systems, but there was no communication involved with those. We saw the first driverless communication-based train control system in Vancouver in 1986. And that was the first use of communication technology, although it was actually low-speed communication. And then we see the pace of change starting to increase. In 2003, we saw the first radio-based system in Singapore, followed by 2004, where we saw the first use of Wi-Fi. And Wi-Fi has remained the dominant form of communication for signaling systems up to very recently. And in fact, up until 2006, fixed block systems were the dominant form of control system for transit. And then we saw a very, very abrupt change where most technology to almost all technology is based on communications. And in those years, we've seen a growth in other services associated with the signaling systems, health monitoring, diagnostics, train to wayside video. And we're seeing that those up to today have been primarily served by Wi-Fi type of systems, but with separate radio systems for CBTC versus other services. Now, recently, we've seen the growth and interest in the use of LTE, and I'm going to go into some subsequent slides to show you what is going on. But you can see that very recently in 2019, we had the first LTE-based deployment, and that's in China. But what we're coming to is, I think we're going to see that there's a significant transformation. So let's look at the market trends. So there's a significant growth in the number of automated and fully driverless systems, and that pace of deployment of these systems is accelerating worldwide. And why is that? Well, driverless systems improve the availability for transit, they improve the performance, and they reduce operating and maintenance costs. However, when you have a driverless system, the overall transit system has to be extremely reliable. In the event of errors, delays can be significant. So the effect of access to data is really, really important to ensure that these systems work extremely reliably. And of course, communication systems are critical to move that data around the system. So there are other megatrends that we see that are also impacting the transit industry. Of course, both edge and cloud computing. We'll see how autonomy is moving over from the automotive sphere into transit. Of course, cybersecurity, Internet of Things, big data, AI, and more. So all of those things are coming actually very rapidly, and they're transforming the industry. Fundamentally, what do the operators want? Well, they want safe, secure, and reliable service. They want to lower their costs. They want to improve their service. They want everything to be seamless and interoperable. And they want new services that can generate new revenue streams for them. So it's not so much about the technology. They're not chasing technology. They want these things. And it happens to be that some of the new capabilities really support these goals. And of course, where does 5G come in? Well, I'll give some use cases in the following slides, but the potential of low latency, high throughput, resilience, and new services that can be connected are all enablers for some of the changes coming. And across the board, we have data-driven operations, of course, for passengers, connected journeys. I think if any of you go in some subway systems, particularly in North America, that's not something that can be taken for granted today. We use the new communication systems to enhance train-centric control with autonomy services. Smart infrastructure allows us to improve the overall reliability of the entire transit systems. Allowing third-party access in provides additional services. And of course, it all has to be underpinned with cybersecurity. I'm going to look at the growth of autonomy in this solution and where that's going and how autonomy and big data and communications are all interrelated. So we're on this journey right now of bringing in new technology coming from the automotive sphere to provide new forms of positioning, providing the capabilities of the trains to react to their surroundings, which improves the solution. And eventually the roadmap moves forward into providing autonomy at all levels of transit operation to improve the overall services. And in order to do that, we rely upon communications to different systems. We rely upon the analysis of the enormous amounts of data that are collected by the system. And we'll rely upon AI to help us make sense of all of that data. So when we look at the current communication-based train technology, the systems are what we would call automated, and they rely heavily upon track and wayside infrastructure. The trains are effectively, they're blind, and they're getting information either from the wayside or from human operators if there's any kind of issue and we need to recover service. As we move forward, you see the same sensor technology as in the autonomous car industry. We have scene and vision sensors, cameras, LiDARs, radars, ultra-wideband sensors, and we remove wayside infrastructure. So we're putting the intelligence on board the train, and this allows new and more flexible ways of rolling out the technology. In fact, when you compare autonomous transit to autonomous cars, although the requirements are in fact higher for autonomous transit in terms of reliability and safety, there is limited infrastructure. Reference maps are feasible. The access is restricted. The scenes are less complex. Basically, we're looking out the front and the rear of the train. And we will, I believe, see that autonomous transit, although it has unique challenges, is going to be in place before we see fully autonomous cars. And with that autonomous transit, with all of those vision sensors, we're also seeing a huge increase in demand for communication throughput. But let's look at some of the other changes that are coming in terms of remote operations. And we've seen this particularly with COVID-19, that there's actually an acceleration in the demand for these new types of services. And anything from remote control center operations, moving away from dedicated workstations in a dedicated network to web and tablet-based operations, fully remote operations. Some operators have expressed the desire to have people work remotely. Cloud services, huge amounts of data that are being collected and consolidated. Big data analysis, operators are in fact asking for real-time big data analysis, which is quite a challenge. Remote train operations, this is seen both as a means of providing train recovery for existing driverless systems, but also to augment those autonomous train operational scenarios. And of course, if we can have remote train operation, it does represent a life cycle cost improvement if those remote operators can be used to support larger fleets for on-demand purposes. And of course, remote technician support, it's an opportunity to provide expertise while minimizing travel. And that's of course, particularly relevant right now. It can be on demand, so there are digital support opportunities that also arise from this technology. Another interesting area of expanded interest is video content analysis. And that can be anything from monitoring the inside of passenger cars, crowd monitoring in particular with COVID, seeing if people are asleep on cars when they go into depots, intrusion detection, vandalism, and so on. And this type of technology actually involves sensors on the train, edge computing on the train, but a lot of data transfer to back-end processors that do some of the deep kind of analysis of the scenes. And what operators are looking for is both counts of passengers in cars to this rapid ability to identify abnormal scenarios and to be able to guide responses to those situations. Of course, cybersecurity is key to all of these systems working and to any deployment. So transit networks are critical infrastructure. They have very high availability requirements, typically at least 99.99%. But until recently, most operators took kind of a naive approach to cybersecurity, so-called security by obscurity. However, with a number of incidents that have been happening, operators are becoming very sensitized to their vulnerability. Just recently, we had a scenario in San Francisco where they were held for ransom with their ticketing system. I've seen that has just occurred in Montreal, but there have been other incidents. This is something where the transit operators are very aware of the risks, and open networks would certainly be seen by them as a source of risk. So the needs for cybersecurity are going to be very high. So there was a brief walkthrough of the trends that are coming, and it sets up my colleague Boyan to explain some of the changes that are coming technologically, but this evolution is occurring in the transit industry. The pace of evolution is increasing. There are great opportunities for new benefits for operators, both operationally and for life cycle cost, and data and communication services are the new enablers.
Thank you, Walter, for sharing those provoking thoughts on 5G urban rail use cases. Let's change tracks for a moment with a poll question. Do you think that public LTE 5G can provide the availability and security needed for mass transit? All right, well, let's see what everyone had to say. 81% of you were yes, and so that makes me think that there's not going to be much marketing effort required to get public acceptance of 5G for urban rail. I'd like to welcome back Boyan Sabasic, our next speaker. Boyan is the Principal Product Line Architect for Data Communication Systems at Thales Canada. He will review future mobile communication options, how to best leverage 5G, and the challenges in transforming from legacy communication systems. We're ready for you, Boyan.
So to continue on my colleague Walter Quinio presentation, one of the key things to consider when we are talking about applying the 5G, it's understanding motivation factors, why we should and why someone should think about potentially applying the 5G to the urban railway. So as Walter quickly mentioned, the number of applications and services is growing. This is the poll that we have in railway industry that show that between 2016 and 2019, number of the services and applications that customers, transportation customers are now mentioning and requiring and considering important in their systems is significantly growing. In Thales, the IoT is something that we are jokingly calling Internet of the Smart Trains. And when we are talking about the Internet of the Smart Trains, we can broadly divide the IoT or Internet of the Smart Trains into 4 large groups of the applications and services. Communication systems that include train to ground, train to train communication, intercar, etc. Service and requirements like voice to the train, data, railway specific services, general broadband communication, information services to passengers, etc. Train control type of the applications related to signaling, safety, and automated train operation. And also something similar to what the other industries and verticals are mentioning and considering, industrial IoT type of the application that are related to predictive maintenance, asset monitoring, energy, improvement of the energy efficiency, improvements of operations, video surveillance, etc. The trains itself are becoming a very complex, considering the number of devices, networking elements, routers, switches that are getting installed on them. So train itself is a one complex network. This needs for advanced networking, multi-services, multi-application support, it's growing not only in urban railway, it's actually a trend that is visible in many other verticals in industry. You can hear about Industry 4.0. We can talk about the applications on airports, container ports, transportation hubs, applications in oil and gas for oil platforms, mining, construction sites, temporary sites. So this need for advanced networking and solutions is not unique to urban railway. It's actually a common theme in many industrial verticals today. So specific to urban railway, we in Thales identifying following needs that are going to be important for us and our customers going forward. Support for multiple services and applications over one unified network, improved range of communication and interference management, positioning and train-centric automated train operation, capability to implement full FCAPS and O&M support in those networks, low latency, scalability of these networks, security, and also something that is very important, and it happens many, many times in urban railway deployment. This is the need and ability to deploy faster and smoother the new networks, new signaling equipment in the existing brownfield installation. So we need the solutions that will allow us faster and smoother migration from the legacy systems to new systems and enable faster, quicker, and better deployment. Before we start talking about details of 5G in urban railway, it's important to understand a little bit about the urban railway communication networks evolution. In urban railway, radio access networks solutions were historically based on some form of IEEE 802.11. Was it FHSS or OFDM, or even CDMA, direct spread spectrum sequence type of the technology? Compatibility and interoperability at the RAN level simply did not exist. Urban railway radio access networks are typically and primarily deployed in unlicensed frequency bands so far. We see now issues related to interference as a result of the general popularity of the wireless access that grew exponentially. And now we have around the world numbers of cases where the interference between unlicensed Wi-Fi access points and the railway deployed networks in the same frequency band is occurring. Attempts to utilize and standardize technology like a GSM-R for urban railway that exists in a dedicated frequency band as defined in European Union and some other countries were not successful in urban railway. And main reasons for that were that GSM-R was not satisfying the needs of urban railway CBTC, communication-based train control in terms of the capacity and latency, and also that the GSM-R type of the networks were very expensive at the time for a typical urban railway deployment. Transport and backhaul networks in these kind of the deployments are typically basic plain vanilla layer 2 and layer 3, and in many cases almost regularly requires dedicated fiber network installation. And as Walter mentioned, security was a bit of an afterthought. What is happening today and what we are observing, it's an increased recognition and awareness of the operators, transportation operators, to operate a railway radio access network in dedicated frequency band for mission critical applications like CBTC as a prerequisite to achieve desired level of availability and reliability. Similar trends we can see in other verticals. Utility market in the United States, who heavily was licensing recently CBRS spectrum, etc., or in some other countries where we see industrial companies now accessing and participating in the spectrum bids and acquiring the spectrum. In European Union, one of the very important things to realize and mention to everyone that the European Communication Commission and ETSI approved in March of 2020 use of 20 megahertz of the spectrum in 5.915 to 5.935 gigahertz for urban railways, part of the intelligent transportation systems. In UITP in Europe as well made the decision to accept 5G as a future standard for future railway mobile communication systems. And they have started definition of the transition plan from the GSM-R to 5G. China, Korea, Australia are example of the countries that are already allocated frequency bands for high-speed railway and urban railway for private 4G and 5G radio access network implementation. Availability of the industrial frequency band suitable for deployment of private radio access network like CBRS in the United States, or industrial frequency band in 3.7 to 3.8 gigahertz in Germany. It is especially interesting to mention that licensing fees for this industrial band in Germany are actually set in a very attractive fashion, and it is not something that will cost millions and millions of dollars. It's a formula that they're providing, allows the type of the companies that want a private campus type of the deployment to deploy the networks in a very effective and efficient fashion. Generally, there is a growing interest for private LTE in urban railway. However, truth is that question of the spectrum, cost, and maintenance are some of the major hurdles, and this is not the same everywhere. It's changing from country to country. Capgemini poll in 2019, it's also interesting, showing how the interest for private licensing per country is changing. And some countries, you have a significant number of companies expressing interest to acquire the spectrum and operate their private networks. Leading countries would be US, France, and in some other countries, there is not that much of the interest at this moment for this kind of deployments. 5G is quickly maturing and proving key technical benefits in real private network deployments. There was recently a very interesting report and webinar from Lufthansa, where Lufthansa was demonstrating and explaining the benefits of the private 5G network that they have done in Germany. We are witnessing the trials of the private 5G in industrial environments by Bosch, BMW, etc. General trend to virtualization, starting with the data centers, railway data centers, OCC and BOCC. And this is also something that is very interesting because this trend to virtualization fits very, very well with the 5G network function virtualization and open RAN, open radio access network. increased trend and recognition of benefit of train-to-train communications, either using ITS G5 or CV2X version for automated train operation, as Walter was mentioning. 60 gigahertz millimeter wave for communication needs in railway. This is very interesting. We see products appearing for intercar communications, fiber backhaul replacement. We actually, Thales has deployed and tested the 60 gigahertz millimeter wave to use for a backhaul in New York Corona Depot very successfully. Another interesting trend is utilization of the wireless communication systems for positioning. So new features now available with Wi-Fi, fine measurement RTT and an angle of arrival, 5G, who significantly improved on the positioning capabilities, UWB, etc. So considering all this, where the 5G private networks and open RAN type of the networks are fit into the urban railway. So just briefly to kind of reflect on what were the private network and private LTE networks up to date. Those type of the networks typically consisted of eNodeBs, EPC, and content server. And in many scenarios, they were deployed in factories, some cases railways, airports, public protection, disaster reliefs, and enterprises. Simplified core, it was the main driver of the initial LTE private networks. It was possible to host a private EPC locally on a relatively small and cost-effective type of the x86 based solutions. And it was designed primarily for standalone as isolated solutions for enterprise or factory kind of the situation. Those kind of the networks in general had a little or no interaction with any public network, and emergency calls in general could not be initiated on this network. And basically they were designed for a network in a box kind of a solution. Going with the 5G and release 16 of LTE, the 3GPP technical specification 26261, it's defining number of the features and requirements in relation to so-called non-public networks. So in 5G terms, non-public networks are intended for the sole use of private entities such as an enterprise, and may be deployed in a variety of the configurations, utilizing virtual and physical elements. They identifying that they may be deployed as a completely standalone and isolated networks. They may be hosted by mobile network operators, PLMN, or they may be offered as a slice of the PLMN. And this is one of the very critical things to understand with 5G. One can achieve the benefits of the private network in many different ways. In addition, 5G supports for time-sensitive communications by seamlessly integrating the 5G system as a bridge to IEEE time-sensitive networks, and general 5G local area network type of the services are something that are of very interesting and potentially can be very important in the future for the railway industry as well. On this slide, we see generalized architecture of the 5G network. A critical thing to understand also that 5G stopped defining nodes of the network, like previous generation of the standards, 2G, 3G, etc. 5G is defining specific network functions. And this approach to standardization, it's very susceptible to implementation of virtualized type of the solution, especially in the core. LAN type of the services, especially interesting, and there is significant number of enhancements. A couple of them I will emphasize here, and that could be important and could be considered very important by our customers. This means that in those kind of the private LTE type of the deployments, unauthorized UE devices, those that are not associated with the enterprise, will not attempt to access the non-public network. And UEs of enterprise will not attempt to access a network that they are not authorized to access. another very important thing to not go through every bullet on this slide is that 5G systems will be able to restrict private communications within a 5G LAN virtual network based on UE's location. And when the UEs move out of the area that are predefined, it will not be longer able to communicate on 5G LAN via network. This is also something very interesting, and we consider this improvements to general security features of the private type of the networks based on the 5G technology. There are many other new capabilities and features and enhancements that 5G is bringing in relation to the LAN type of the services, which could be a completely separate presentation and webinar just on that. So this is something that is very important to understand, and this is different models of achieving and deploying the 5G private network. So on one side, you can start with a completely privately built and owned network, which has its own cons and pros. One of the biggest of negatives is the obviously high capital expenditure for software, hardware, and license fees. Spectrum cost in some countries, this may be high. In some countries, the spectrum maybe already exists, or in some countries, the spectrum is becoming available under a different type of the licensing scheme. So it's not the same story everywhere. And depending on the geography, question of the spectrum should be differently treated. Potentially, it will be difficult to find the IT staff that will, and one would need help from integrators. That also adds to the CAPEX and OPEX. But to the other side, this kind of the networks are, if someone really is requiring that, are completely isolated from public networks. QoS and QoE is independent of the public networks and controlled internally. Data are stored locally. Ultra low latency is possible, and there are no monthly subscription fees and charges for this kind of a deployment. The similar to that will be deployment where the network is deployed and built by MNO and then operated under SLA agreement. Again, there are pluses and minuses of that approach. For the sake of time, we cannot go to the details of that, but just to quickly mention, important to mention all these different type of the possibilities. There is possibility to deploy the private networks utilizing a RAN sharing approach, where only the radio access network is shared with the service provider. That reduces the cost, but introduces some dependency on the MNO, but definitely it's possible. And possibility to deploy it utilizing complete radio access network and control plane sharing between the private 5G network and the MNO type of the network. Again, different type of pluses and minuses for that type of the application. And finally, slicing, where it's something that due to this virtualization concept and 5G standardization effort in regards to this kind of the features and capabilities, it's possible to effectively obtain virtually the 5G private network at the premises through the 5G slice. Obviously, benefit of something like that is the lowest capital expenditure, lowest cost of getting this done, but there are obviously dependencies on the service provider and the MNO spectrum in that case. So important thing to mention and understand that there are the variety of modes and ability to deploy 5G type of the network for the private needs are with 5G bigger, higher, and better than anything that we had in the past. From standalone to the hybrid type of the private networks to virtual private networks with the slicing. So there is multiple options here to choose from. One size doesn't fit all. But the key point to remember that 5G is bringing all the tools required, and technology is in the place to enable variety of type of the deployments and scenarios for the needs in the private network. Open RAN is another interesting thing when we are talking about the private, not only private, general 5G networks, which is the tendency and shift to more open implementation of the 5G network, where the specific functional layers and network functions are deployed on x86 type of the hardware, and the interfaces between these components are well defined and standardized through 3GPP and O-RAN alliance. And this approach to solution of deployment, for example, standalone 5G, isolated 5G network, utilizing Open RAN architecture is very, very interesting. And in our opinion, it fits very well with the private LTE type of the deployments. Benefits are, most of the hardware is based on the COTS x86 hardware. Software stack is coming from a number of software vendors that are increasingly growing and forming this ecosystem. Radio remote units are already, we have 4 or 5 different vendors in this ecosystem, and the number is further growing. Performance, Open RAN and deployment of the Open RAN type of the networks in urban railway is a very interesting thing because it provides a concept of so-called shared cell. And this shared cell architecture is a very interesting in urban railway because it virtually eliminates the handover. Long-term support, this may be one of the most interesting things in relation to 5G and O-RAN because it's based on ecosystem of the vendors. So from the long-term support perspective, our customers can be assured that this ecosystem will be able to support their products deployed in their environments for a very long period of time. Integration and maintenance is one of the key points with the O-RAN type of the deployments. And this is the area where Thales can help our customers. This is the area that we are looking to invest and develop our skills and help our customers to potentially be able to deploy 5G private networks utilizing Open RAN architecture. Again, for the sake of the time, all these things that we are mentioning obviously are touching in so many different areas, and these new networks providing so many capabilities, so many new capabilities and advantages over what has been done historically so far. To touch upon maybe just a few, real-time data collection, telemetry provides the most important component in our opinion for future AI-based maintenance and diagnostics. New wireless networks based on LTE 4 or 5G and Cisco Fluid Mesh, which Thales is also working with, offer significant improvements in the throughput, range, and much better mobility and handover performance, etc. Also one important thing to take in account, the 5G itself supports heterogeneous networks. And the heterogeneous network could be a very important concept going forward because as we said before, one size doesn't fit all. And sometimes there is a combination, and maybe the best and most optimal way to deploy radio access network is combining private-public network. And the 5G, it's actually providing a lot of tools and options to deploy this type of the heterogeneous solutions. And it could be something very important for urban railway going forward. Quickly, just to show some of the things that we are developing in Thales. We are developing a new generation of the mobile communication gateway, specifically designed for the urban railway. It's a ruggedized x86 platform approved for the railway type of the application. We can support large number of different types of the radio access network connectivity in terms of the 4G and 5G. This is Thales Gemalto 4G and 5G LTE modules. We can support Wi-Fi 802.11ac or AX. or even 802.11p DCRC or CV2X type of the communication with this new communication gateway. We providing additional capability for real-time telemetry utilizing this gateway that will be deployed on the train. Virtualization is supported on this platform, so we can develop or allow our customers even to deploy potentially some of their applications utilizing containerized Docker environment that we are running on this platform. One other things that we are preparing in Thales in Toronto, it's the 5G Open RAN testbed that we will be developing as a part of our Encore involvement. And the next year, we are planning to deploy and have the 5G O-RAN testbed, most likely in a 3.5 gigahertz frequency band operating in Thales, Toronto, where we can perform additional testing, demonstration, integration. And this is something that we consider very exciting because it will be serving us as a breeding ground for developing new ideas in relation of how to best utilize the 5G network in the urban railway. Again, to conclude, use cases for 5G, unified train-to-grind network, positioning, it's also something that we are expecting to be a very important feature coming from 5G that we could use in the urban railway, train-to-train type of the communications, and train-to-infrastructure type of the communications. Those four groups are probably something that is the most important to mention and conclude at this point that we consider that 5G will bring to the table when we are talking about the urban railway. At this point, I will conclude my presentation. I think I've run a little bit over. I apologize for that.
Thank you, Boyan, for helping us understand how 5G latency, scalability, and security capabilities meet the needs of urban rail. It's time for another poll question. Do you think that rail operators in your geography will want private LTE 5G or network slicing over public LTE 5G? Well, let's look at the results. Well, it looks like private has it. I guess that means that the unlicensed bands are probably going to be sufficient for urban rail needs, at least as this audience sees. I'd like to welcome back Chris Neisinger, our next speaker. Chris is the Chief Technology Officer at Guavus. He will discuss how mobile network operators can help urban rail transit operators get the greatest value from 5G by improving services, security, and customer experience. Take it away, Chris.
I took this same slide from Boyan, but expanded on it a little bit, just to reiterate the point that these smart trains are very complex. They're basically small data centers moving around the city, and edge processing and edge analytics on the train are really required to enable some of these low latency sensitive applications. So it is going to be important, and I believe Boyan showed one of his last slides where we're showing the edge processing and on the communications module. We believe this is very important to start the analytics at the edge as well as the communications. The other point is that the urban rail systems themselves are complex, with thousands of smart trains. The need for private and secure redundant data centers on site. I think that these are being designed to look at security and reliability as well, and then integration with open systems like public and private cloud solutions. So again, these are technically sophisticated, complex networks, and the communications infrastructure to support them is becoming as complex as a small telecom operator's whole network. And that puts the urban rail operator in a position where they need to be experts in rail and also experts in information and communications technology. It's kind of difficult to do everything, but let's look at that requirement for security, reliability, safety, and we mentioned train to ground, train to train, train to infrastructure, a communication system in the stations and wayside. On-premise data centers. It is very, very, very complex network, and the rail operators, the urban rail operators, being communication experts as well is difficult. So what's required to make a world-class communications network? And I've listed 4 things here with technology, infrastructure, systems, and processes. The complexity that these bring, you need to have an AI ML centric way of reducing that complexity to deliver the solutions that you need to deliver. One of the discussions of reliability, of 5 nines reliability, is thrown out all the time, and just realizing that 5 nines reliability means 6 minutes or less than 6 minutes of downtime a year. So if you're dealing with an issue with only 6 minutes of downtime, you better be able to predict the outages happening, have a solution to that, and start implementing the repair to the solution actually before the outage happens. It's the only way you can meet these kind of reliability requirements. So without an AI ML based approach, it's just impossible to meet those. I'm going to skip through that and get right into a couple of the examples of that we've used at Guavus. So basically, we're trying to leverage, or we are leveraging the telecom solutions that we have developed for large tier 1 telcos and bring those same capabilities to urban rail. So this first process I'm going to explain, I'm going to explain a couple of them. This first one is just multi-domain root cause and likely fix analysis. So on this slide, you'll see on the left side, this patchwork is really to represent the multiple data sources with event tickets, syslog from network elements, alarms from equipment on wayside, positioning information of trains, just all of the type of data that's available, and looking across that the different domains. So each train could be seen as a simple its own domain. The track itself is a domain. The service that is being looked at is a domain. And so the first portion of this this triage is to make sense of that data, to sessionize the data, and look at related data independently and then across the multiple domains. So what we do with this behavioral analytics is we do that, and we look at the different layers to find out, is there something related to all the layers that can help find the likely root cause. So an example here would be on the trains themselves, and the smart trains would have some wheel slip detectors looking at when there was wheel slip, what is the condition of the train at that time, what's the speed, what's the location on the track. And if this is only happening in one domain, on one train, it's likely a problem on the train with the train systems themselves. If it's happening on multiple trains, but at different points on the track, it's likely an issue of the control systems on the trains. If it is multiple trains and always happening on similar positions in the track, this can be considered a problem on the track. So this is a simple example of how looking at the different domains can help isolate where the problem is. Is it a train problem? Is it a track problem? Is it an other deep-seated problem? That this is a simple solution with just looking at 3 domains. The AI ML big data approach allows us to look at multiple domains at all times to find out what is the likely root cause. Another point I want to bring up here is a concept called explainable AI, where this evidence of what is wrong you need to have the why as well. Especially in networks like this, understanding the why is just as important to be able to get to the fix. So we're always collecting the evidence of all these multiple domains to indicate this is likely what's wrong, this is what will fix it, and here is how we came to that conclusion. So all of those are included in this this triage and recommendation and machine learning. A second aspect is predictive operations. Again, we start with the same point of logs and performance metrics of all the disparate data sources. We use behavioral analytics to group those. So we would look at common elements and look at the performance of common elements to predict the performance of that. And we look at each individual asset separately. We don't look at a collection of assets. Each individual asset gets its own score. And by looking at this score, we can determine which device is likely to fail first, when preventative maintenance should be done. Now, predictive operations is often looked at just as outage prevention, and that's a good thing. That's increasing reliability. Outage prevention is great, but also predictive operations allows us to do just-in-time maintenance and just the right amount of maintenance. So we're trying to extend the life of an asset and reduce the maintenance costs. So we just don't project standard rules-based maintenance like in your car, where you get to maintain your change your oil every 5,000 miles. Sometimes it should be 8,000 miles. Sometimes it should be 4,000 miles. And you know, the manufacturer of the vehicle says just do an average. When you do an average, half the time you should be doing it earlier, half the time you should be doing it later. So average planning is just that, average. So what we're looking at with the big data approach is you look at each individual asset and look at what load has been on that asset, how has that asset performed, how has it performed versus its peer group, and you can get a reduction of outages because you can predict those and prevent them. Also, you get an extended life of the asset with the reduced maintenance. So it both increases the efficiency and reduces the cost. So value creation with the AI and ML is really what everything's about. So value creation for the urban rail operators, all in the area of reliability, efficiency, quality, and performance. And I've listed just a handful here. When doing an AI ML program, an analytics-based program towards something like urban rail, the objective is to find value in all of these areas that they're interested in, not just focus on one, because you'll find that a solution in performance may also, with a small twist, become a solution in reliability. So the performance of urban rail to increase the identifying, for instance, track segments of concern that might be causing noise in the cabins, and people look at that as I want to increase my performance, make my trains quieter for the customers. That's also an indicator, obviously, of an issue that could affect reliability. So looking at all of these different tiers and finding value in all of them is very important to the overall success of the program. And also don't lose sight of the fact that that there's value for the customers as well. It's not just about making efficient, safe, reliable solutions for the rail operators. It's for the passengers, and I think there was mention of better service, connected journeys, more seamless support going through things like breeze-through recognition at the stations, enhanced automation, and personal services that will also give the urban rail operators an opportunity to have value-added services for both customers, just enjoyment, and as also monetization efforts in this space.
Thank you, Chris, for sharing the network operator perspective on 5G and urban rail. There's definitely a lot to consider there. I know you've all been waiting for it, so it's time for another poll. Do you think that AI/ML with O-RAN 5G will be important for urban rail applications? All right, I'm closing the poll. Let's take a look at the results. This is what we expected. Thales really looks forward to helping you develop those solutions. All right, I'd like to open a question and answer session. Please be sure to send your questions using the webinar chat. And I ask Walter, Chris, and Boyan to restart their audio and video at this point. And we do have a first question that I'd like to address to Boyan. And the question for you, Boyan, is if the existing Wi-Fi based communication systems work, Why would conservative transit operators want to switch to 5G?
It's a very good question, and the question depends on capability of the existing system to support all the new type of the applications that are coming. So do you have that quality of service and quality of the experience with the existing Wi-Fi system to enable you all these kind of the applications that we were talking about today? That is one critical thing. The other critical thing to consider is some of the advanced capabilities of the 5G, like I mentioned, time-sensitive networking, which can become a very important in some type of the applications that we are planning to implement in the future, which will be very difficult to implement over Wi-Fi type of the networks. And the 5G TSN capability, it's a crucial in that aspect. And applications and specifically related to the positioning. And 5G is already, like a few months ago, Qualcomm started demonstrating 5G positioning capability, where they demonstrated sub-meter, actually centimeter type of the positioning with the 5G type of the solution. So answer is not simple. It's one has to understand what is the future for these customers, what do they want to do in the future, and clearly understand, does the existing systems are capable to support the future needs or not?
Thank you, Boyan. A question for you, Walter. When do we expect the urban rail market to switch their preferences to LTE 5G?
Well, I think we already see that shift is starting. I mean, we have one line now where we have a hybrid solution where the primary communication system is Wi-Fi, but the transit operator is using LTE as a backup communication system. We're also seeing new, in one of the sites, the approach being taken is to use public operators to provide the communication services, and their approach to achieving the availability is to work together with several different operators. So I think what we saw before was a pretty rapid shift from no communication to Wi-Fi, but I think with all of the services, particularly with those drivers that I mentioned before, all these other things coming, the digital services, the telemetry, the ability to reduce costs, within the next couple of years, we'll see actually many, many more operators that are pushing for LTE and 5G based communication systems.
Thanks, Walter. I think we have time for one last question. Chris, when do you expect the 5G private mobile network market to take off?
So as Walter was saying, you know, the push right now is to leverage the 4G LTE networks. I think the operators would go to 5G if the networks were available. So, you know, we're seeing different rates across different adoption of 5G across the globe. It's going to be dependent on the operators and the push. In North America, the move to 5G is very rapid. Other areas it'll come a little bit slower, but we're seeing in all parts of the world, 5G is definitely the infrastructure of the future, and we will see pretty significant deployments in 2021 and beyond.
Thank you, Chris. I'd like to thank everyone who participated today. As soon as the webinar closes, you will receive a survey on screen. We hope that you can spare a few moments to provide us with your feedback. That feedback is quite valuable, and we use it to shape future webinars. Also, please be on the lookout for details on our next webinar scheduled for December 2nd, 2020. Thank you.